We would like to introduce our E2 GAN for efficient and effective GAN architecture search. GAN have been successfully applied to a wide range of generation tasks, including image generation, image translation, and many other tasks. While designing favorable neural architectures of GANs has made great success, it typically requires a large amount of time, effort, and domain expertise. To alleviate this network engineering pain, an efficient, automated architecture searching framework for GAN is highly needed. Neural architecture search methods have the potential to largely alleviate this burden by automatically search for a good architecture. So these NAS approaches have been applied and proved effective in discriminative tasks such as image classification and segmentation. Methods are being actively proposed in the field of NAS. They often fall into categories of evolution algorithms, gradient-based, or reinforcement learning-based approaches. In this work, we focus on the reinforcement learning NAS approach, and we specifically target GAN architecture search problem. Reinforcement learning methods aim to find an architecture from the search space by following a search strategy that will maximize the performance. The earlier methods often formulated architecture search as a single-step decision process. For each step, a sampling is done for the entire architecture by the agent, and the evaluation is then conducted for this sampled architecture to get the reward. And the reward is then used for the agent to learn a better policy. And since the sampling is done over the entire architecture, this often results in high-dimensional action space, which further leads to increasing search time and potential optimization difficulty. To improve efficiency, many NAS methods make use of the macro architectures. And in this setup, a handcrafted macro architecture is predefined. The outer structure is thus fixed, and agent only search for the cell architectures. And this means that the search is done only on cell levels without taking the correlation between them into account. And this can lead to suboptimal performance when evaluating on the entire architecture. Similar ideas have been adopted for GANs. In the recent work on GAN architecture search, AutoGAN adopted a hierarchical search algorithm. The search is done on the cell level, layer by layer, in a greedy fashion. For each cell, an architecture is chosen to optimize the current layer's performance without considering future layers. Once decided, the architecture of the cell is fixed, and the search continues on the next layer. These greedy methods decrease effective action space and speeds up the search. However, the improved efficiency comes at a cost. In AutoGAN, the GAN architecture of individual layers is decided greedily without considering subsequent layers. However, a better architecture may have a lower reward for the first layer, but a higher final reward for the entire architecture. Therefore, we ask ourselves, is it possible to target both better efficiency and effectiveness? Specifically, are we able to speed up the search and still consider the performance of the entire architecture? We find the characteristics of GANs very useful to answer this question. We're especially inspired by the success of progressive GAN, whose key idea is to start from a low resolution and progressively model increasingly fine details in further layers. Given this property, we believe that the design process of a GAN can be modeled as a multi-step decision-making process. Thus, we reformulate it as a Markov decision process problem. A MDP is a discrete time stochastic control process, and at each time step, the process is in some state, and its associate decision maker chooses an available action based on the state. And given the action, the process moves into a new state as the next step. So here is the decision-making module. In each step, the agent observes the state information described by progressive state representation. Through the policy network, the agent will make the decision and output the cell architecture in order to get high reward. Then the cell will be added to the current architecture, and then state information will be updated for the next step. And this process goes on until we reach the predefined depths. Since we reformulated the problem as a Markov decision process, an informative state is needed. Inspired by progressive GAN, which has shown to improve generation quality in intermediate RGB outputs, we propose a progressive state representation for the GAN architecture search. Specifically, given a fixed batch of input noise, we adopt the average output of each cell as the progressive state representation, we downsample this representation to impose a constant size across different cells. In reinforcement learning, the agent will learn things and update the policy according to the reward. We propose to design the reward function as a performance improvement after adding the new cell. And in this work, we used both inception score and the FID as indicator for the network performance. Under this formulation, the cumulative reward then becomes the performance of the entire architecture. We can have a quick comparison with AutoGAN, where layers are determined greedily, and the optimization only considers the current layer's performance. By employing the performance improvement in each step instead of only using performance as proposed in AutoGAN, our method can maximize the expected sum of rewards over the entire trajectory, and this enables us to target a potential global optimal solution with the highest reward in the end. The proposed design of state, reward, and action fulfills the criteria of Markov decision process and makes it possible to stabilize the training using off-policy samples. We are now free to choose any off-policy IR solver to further improve data efficiency. Comparing to off-policy methods, previous on-policy IR approaches requires a frequent sampling of cells generated by current policy to update the network. Moreover, new samples are required and to be collected for each gradient step, while the previous batches are directly disposed of. And this quickly becomes very expensive as the number of gradient steps and samples increases with the complexity of the task. By comparison, off-policy reinforcement learning algorithms make use of past experience such that the RL agents are enabled to learn more efficiently. Here we maintain a memory buffer to learn from the past. Regarding the implementation, to verify the effectiveness of the off-policy framework and to enable a fair comparison, we use the same search space as used in AutoGAN experiments. We adopted the SAC as the off-policy reinforcement learning algorithm. We use a CIFAR-10 dataset to evaluate our framework. We use its training set without any data augmentation techniques to search for the architecture with the highest cumulative return for a GAN generator. So here is the generator architecture discovered by E2GAN on the CIFAR-10 training set. By searching with multiple seeds, several notable observations could be summarized. First, it prefers post-activation convolution to pre-activation convolution, and this finding is contrary to AutoGAN's preference, but coincides with previous experience from human experts. Secondly, it prefers the use of batch normalization, and this finding is also contrary to AutoGAN's choice, but is in line with experts' common practice. And finally, it prefers bilinear upsample to nearest neighbor upsample, and this in theory provides a final upsample ability between different cells. We trained the discovered E2GAN from scratch for 500 epochs, and our model achieves a highly competitive FID 11.26 compared to the published results by AutoGAN and handcrafted GANs. In terms of inception score, an E2GAN is also highly competitive. We also transferred the discovered architecture to STL10, and the performance is also significantly better than AutoGAN. And this proves that E2GAN is able to find highly competitive architectures using much shorter time. We train our agent over 3 different seeds. As shown in the figure, we observe that E2GAN can find similar architectures with good performance on the proxy task. We compare our method with a non-MDP formulation which greedily decides each cell. We notice that our MDP formulation is able to find a better architecture which has a lower reward for the first layer, but a higher final reward for the entire architecture. Coming back to the question we asked ourselves in the very beginning, can we target both efficiency and effectiveness? And the answer for GAN is yes. To improve efficiency, we propose to use the MDP formulation and the progressive state, which enables the optimization based on the disentangled steps of cell design. We then make use of off-policy reinforcement learning to further improve the efficiency. And to improve effectiveness, we managed to target a good performance of the entire architecture. And this is achieved by using our MDP formulation and using performance improvement as reward. By using the proposed MDP formulation, we are able to find highly competitive architectures in a shorter time. Thanks for listening, and our code is available online.